Brian Keating is conversational, he is kind, he is incredibly well-spoken,
He's a humanist,
has a comprehensive knowledge of the history of science.
understands the human biases that go into science, reluctantly but honestly, and I really, really enjoyed exploring the different cognitive fractures that are bound to befall our pursuit of knowledge in science and the deification of our scientific heroes. And it's just a great conversation. I think you guys are going to love it.
Yeah, he's got 2 books. One is Losing the Nobel Prize. One is Into the Impossible. And they are both the basis for a lot of what we talk about. So they're linked in the description. If you want to support us and Brian Keating, you can buy them. If you want to do more for the podcast, you can join our Patreon. We're at patreon.com/demystifysci. You get to come to weekly Patreon chats, so you get a direct relationship to me and Michael Shiloh. And then if you have already done both of those things and you are reaching for what you can do to help us even more, share the podcast. Tell your friends about something amazing that you have found called the Demystify Sci podcast. Enjoy the conversation with Dr. Brian Keating. We will see you next week.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
My brother's skeptical about, he's a professional skeptic. And I was talking to him about the idea that podcasts and YouTube videos are places where it's possible to present new ideas to the scientific community. And he was very skeptical about that idea. He's like, look, text has been the medium for centuries, and it will remain the medium for all serious ideas. And so anything that comes in the format of a video or in the format of a podcast is by default not considered as a serious idea. And I was just wondering, do you agree with that?
Yeah, I disagree with that. I mean, just on a basic level, there's, studies that show that people absorb visual information, 60 times faster than written information. I mean, look, writing has only been around for 3,000 years, 4,000 years at most. And paintings and caves have been around for 200,000 years, right? So there's no comparability between what you can absorb, visually versus audio. That's why, by that logic, no offense to your brother, but then I wouldn't put any charts in my research papers, right? It would all just be, the whole thing is a picture's worth 1,000 words, and the scientific chart, in our case, it could be worth, a petabyte of data. So. Yeah, I disagree with your brother there. I think there's the people that study things like, do you remember an audiobook as much as you remember a printed book, and then a Kindle, versus a printed versus an audio. So those are nuances, but I don't think that there's any doubt you can learn a lot from video. I mean, I rarely read, hard copy stuff that's not, nonfiction. So. I wonder. Yeah, I think that especially as the brain is kind of attuned to visual information, it's natural that we'd get more from audio, etc.
And it's all about communication at the end of the day. Like, you have an idea and you need to get it across, and whether you're Da Vinci encrypting it in code or whether you're just speaking to somebody directly at a live conference or on a podcast, if you have an idea, the idea should be able to stand on its own merits.
But we live in a world that has to do with how your community and how your peers accept your idea, right? Like, science isn't just a place where you can have, sadly, it's not just a place where you can have ideas and fully develop them and have that be evaluated just on its own merits, right? It's evaluated by how well your community accepts it. And if the community doesn't accept the format in which you deliver it, like, it's hard for me to imagine a YouTube video replacing a science paper. But I think that it should. I think that it should be able to. Like, I really do.
There's like this video journal. Are you aware of this? There's some sort of video journal that's coming online.
There is the Journal of Visual Jove.
Oh, Jove.
But that's an experimental technique journal, which I think is useful. It could. But, like, one of the biggest problems with scientific papers is that they're very inaccessible, right?
Mm-hmm.
Like, you read a cosmology paper, you read a physics paper, you read even honestly like biology papers. They're filled with acronyms, they're filled with math, they're filled with not necessarily an attempt to reach their audience. They're just catalogs of ideas.
Well, the audience is really narrow, I guess.
The audience is really narrow, yeah. And so I find that hard to believe that you could have the entire community be willing to shift, because text feels so dignified. It's so old. It's so established. Like, this is how we've always
Yeah,
done
there
it.
are, certainly elements of that. I think, no one would argue that you have to replace text with anything. And of course, you really can't digest, methodology and experimental, kind of technique using just pure audio or video. I mean, that would be, completely impossible. And then, of course, all the reference material, right? I mean, you're going to go back and take Einstein's papers and turn them into videos and then have a reference in the video to that video. I mean, that might get pretty complicated. So I think there's a historical literature. I think that there's a tradition. But I think you can augment it. I think, the explainer type stuff that I do, and that folks like Arvin Ash or Sabina Hassenfelder do, those are really supplementing it. And where I'm trying to fit in my niche is that not many of them are experimentalists. In fact, I don't think there's a single experimentalist that's consistently putting out, physics short videos and explanations for experiments or astronomy results and stuff. There's all tons of theorists, like I mentioned those guys, and someone like Neil deGrasse Tyson or somebody like the rest of them, Professor Dave, they don't really do anything from an experimental point of view. They do great work, but Brian Greene, they're all theorists, Jan Levin. So that's really important, but I think it gives a biased idea. And I think for young people, are we recording, by the way, for the podcast, or are we just kind of chit-chatting? Okay, great.
Our podcast basically kind of chit-chats.
All right, that's fine.
What we do.
You can edit that part out, yeah. I was just getting I was getting some text from my wife who I have to meet in about 50 minutes, so I've got a hard out at 1:15. But what I was saying is, I think those are really valuable. But like you normally you meet somebody and they'll be discouraged because they'll say, I can't be Einstein, I'm not that smart. So first of all, Einstein wasn't always Einstein, right? Einstein was, an ignorant, just because he didn't know as a younger person, and then he developed and became a scientist through training and practice, apprenticeship, hard work, thought, and so forth. But
and collaboration.
Yeah, but
getting
even
along
like
with people.
But the brightest, theorists today, people like Jan Levin or Sabina, they're not Einstein either. But what if they said, oh, I can't be Einstein? Like, there's a difference between, kind of forecast, predicting, projecting your future, and that has a limiting belief overlay on top of it that can really be kind of consequential for a kid to not go into science. Yeah, I interviewed Jim Gates way back when, 2 or 3 years ago, and he said the same thing. Like, people say, I'm no Einstein, and then that prevents them from even attempting A, to be Einstein, but B, we don't need that many Einstein. I made a tweet today about Einstein was wrong at least 7 times in major issues, from the reality and locality of quantum mechanics to the cosmological constant to the static universe, many times. And I always joke it's too bad because he could have had a good career. But no, he did have a good career. But he made blunders too. And they say, typically a theorist only has to be right once in her life to have a famous world-renowned career. An experimentalist only needs to be wrong once to have a storied career or fall apart. So, but I think, the lesson I'm trying to impart in my explanations and so forth is that there's more than just theoretical physics. There's more than just, thinking about wormholes and black holes and, donut holes or whatever. There's a whole vast regime of physics that's called experimental physics, and that in astronomy that people don't really know much about. So I've made that kind of my endeavor to really bring that to the forefront, and I think that's very well suited to the video format. It's very hard to get past a couple of equations and some whiz bang visuals and wormholes and stuff, but it's very straightforward and applicable to show how an experiment works, how even data analysis works, how we account for our errors as a scientist. And I think that's incredibly important. So yeah, all those reasons, I think there's really kind of a big gap in how we present things, and hopefully some of what I'm doing will help to fill it.
Yeah, I mean, I think that the distinction between experimentalist and theorist is something that we talk about a lot.
Yeah.
Right? It's physics seems like it really benefits from experimentation, because experimentation is the place where you see weird things. And the weird things that you see are the things that have to be incorporated into your theories. And so if you have a discipline that shifts entirely to just thinking about what's mathematically possible.
When did the schism occur? Because it seems like it started off as experimental philosophy, and I can't imagine somebody doing theory without experimentation. But then at some point, it's really more obvious in physics than anywhere else. But in biology, there's theoretical biology.
Wasn't it Dirac? Like, I remember always reading that like Dirac was so mathematical and he was so good at putting things into math that everybody just kind of followed him.
Yeah, when did this happen?
Yeah, I would go even farther back. So Galileo is kind of the prototypical scientist, credited with creating the scientific method or applying the scientific method for the first time, and at least in the Western sense. And I really think overall.
Built a really badass telescope.
Yeah. So he didn't invent the telescope, but he perfected it. He took it from, 1 to, 1.5 power to 10 to 20 power, which allowed him to see things that nobody could see before. And so it was really an upgrade, like going from a flip phone to an iPhone 14. It was so dramatically better than anybody had ever done before. And then he could test hypotheses, and he could use the telescope. So I always have there's my camera just collapsed as I'm getting my telescope out.
Yeah.
Okay, hopefully you can edit that.
A spyglass.
Yes, I've got my perspiculum tube there. So he would use it to engage with his theory. So his theory at the time was not really his, it's due to Copernicus, that the sun is the center of the solar system and not the Earth, as had been believed for a long time. And actually, I'd only recently, and we'll get back to this, but I'd only recently discovered why was Galileo, imprisoned for his ideas, if the idea of a heliocentric universe was refuted by supposedly the Bible, but the Bible doesn't actually mention anything about the sun or the moon or the earth or where they're created. And they're created on the fourth day of creation, if you're literalist, but we're not going to get into theology. But the interesting thing to me is, why would the Catholic Church, which is eminently theological in their orientation, why do they care about what Ptolemy and Aristotle, two pagans, thought about what the natural order of the universe was? I mean, they didn't, Aristotle lived 400 years before Jesus. So how could that have any bearing on what the Catholic Church could torture and imprison people over, like Bruno?
Well, they're trying to integrate all of the native pagan populations too, right? And the pagans traditionally have thought of the earth as a plate with this dome of magic over top of them, upon which all of their myths play out. It's like really important to these people to see the world that way. Yeah. So I think the Catholic Church was the state, essentially.
True that Aristotle did think that the earth was a sphere and center of the universe. I mean, so he wasn't a pagan in that exactly. You're exactly correct, but he wasn't a pagan in that sense of accepting a flat plate, but he believed the natural order of perfection was that heavy things fall faster than lighter things, which Galileo proved wrong at the Tower of Pisa, allegedly. But also that the center of everything is perfection, and the center of the universe should be the perfect culmination of creation, which, in his mind was the earth. He believed in, at least one God, but maybe more. But so it turns out that the Catholic Church later effectively baptized Aristotle retroactively, posthumously. So after St. Thomas Aquinas, in Christianity and later Maimonides and Judaism, which I practice, they really kind of had it was like more, than string theory or something. Like, it had to be reconciled with the observations, because an ordinary person could look up and see the sun. It sure does look like it's going around the earth, but so how do we deal with scientific data like Galileo collected? So Galileo collected data, analyzed the data. He also did experiments where he
used that magnificent telescope to check out basically to observe the phases of Venus, which kind of nailed the coffin, I guess.
Yeah, that wasn't the actual ultimate proof, but you're right. He had a preponderance of evidence. So he had the fact that the Jupiter seemed to have 4 little planets, or stars, as he called them, Medicean stars, and they were orbiting around it, not the Earth. So if the Earth was the center of the universe, now you had to tack on, this more and more epicycles. And they did that with Venus. I mean, look, they did it with the sun, right? So it wasn't like Venus presented them with a challenge. But what's so fascinating to me is that Galileo, so he did build experiments. So he had don't forget, like doing this back then, there were no clocks. Like imagine trying to do a lab and there's no timekeeping device. You don't even know what time of day it is. There were no clocks back then in 1620s and 1630s.
There were like water clocks and like sand clocks, and so you could like synchronize things roughly, but again,
Very
like you
rough,
have two
yeah.
different sand clocks and they run at
They
slightly
must have
different
used
times.
something for like that Aristophanes experiment.
Yeah.
Oh yeah, do you have any insight on that?
Yeah, total
So,
Yeah,
so
I have like
that's the-
absolute phase shift right
Tangent.
here.
Yeah,
but-
right.
but
Yeah.
this
So
is-
that's the measurement of the spheres, the curvature of the Earth. So they did it at two locations that were fairly close to one another, and all they needed to know is local noon at that time on a given day. So they really only needed to know the time within, say a few hours. They could measure the height of the sun above the horizon in the middle of the summer, and they would know it's at its maximum elevation or elongation. So from that, they could do that locally. They didn't need to like have synchronized to the second.
basically a
And they
sundial.
just noted that there's a shadow, and the shadow was longer and farther when you were closer to north of Egypt, where they did the measurements. And there's a wonderful video of Carl Sagan who's just like, talk about videos, like explaining things. Like there's phenomenal video. He goes to Luxor or wherever it is and does the experiment, and you just see it, and I'm like, all right, that proves it to me.
That's the one that won me over to Carl Sagan. That was like one of the first videos I saw. I was just like, damn, that is a great way of explaining this. I was just blown away.
Yeah, one of my highlights of podcasting career is I talked to Andrewian and Sasha Sagan, so his widow and his daughter, and just my recollections and inspiration of Carl. But getting back to the experimental versus theoretical. So Galileo was testing the hypothesis that the sun was indeed the center of the universe using observational data from an instrument that he did collect and build. And so, yes, that was an early version of it. And then later on, he would do things like at Pisa with dropping lead cannonballs, and then later he would do stuff with inclined planes, which we think of as really boring, right? Like if you took freshman physics at college, as I actually never did this experiment. I don't know how I skipped it, but I never did it. But I always think it would be so much fun to teach not only the how he did it, but and just get the results, but show how ingenious it was. So you're right. The timekeeping was good to the couple of seconds, maybe with a sand clock or a water clock. But gravity is so fast. If I take this crystal ball that I use to make predictions and I drop it, I mean that you need a couple of fractions of a second of resolution to do that, right? So what did he do? So he made the famous inclined plane, which allowed him to vary the force of gravity, therefore minimizing the time errors on the effect of these balls rolling down inclined planes, allowing him to measure the gravitational constant. So that was an experiment, and he did it. And we do it to this very day. I mean, very few experiments that you can do that were actually done historically that revolutionized our understanding of the universe. Another one is his observation of the moons of Jupiter. So I don't know about you, but I don't have like a large hadron collider lying around my backyard. Although one of my kids wants to build one. Yeah, one of my kids wants to build one. But so you can't actually replicate what Fabiola Giannati, my co-reader on Galileo's dialogue book, she's the director of CERN. So she can command it to do whatever she wants probably, but you guys can't, I can't. So you can't replicate how she felt when she announced the discovery of the Higgs boson back in on July 4th of 2012. So we're kind of immune to that. We have to trust, oh, they look excited, they're crying. There's Peter Higgs, he's crying. My late professor Jerry Guralnick is there, he's crying. But you can exactly replicate what Galileo Galilei felt, another Italian scientist like Fabiola. And you can do that by just getting a telescope and looking at Jupiter or Saturn or Venus's phases or the craters of the moon. So Galileo, getting back to the original question, Galileo felt that you could prove things through observation. And we don't believe that now. We kind of somehow doubt the efficacy of proof by observation, but we recognize it as a key component of the scientific method. And the ultimate culmination of that is when someone replicates it, right? So we trust that someone else can replicate the Large Hadron Collider's results. In fact, there are two experiments that both got independent confirmation of the Higgs boson's reality. One is called the CMS, or Compact Muon Solenoid. The other one was called Atlas. They both saw the exact same result. two different, completely independent rival teams, which is kind of important, and they both saw something completely different. None of them won the Nobel Prize, by the way. So that's kind of one of my bugbears in my first book, losing the Nobel Prize, but we'll talk about that later. So yeah, so the experimental input is often overlooked. And it's sort of like, well, we'll just serendipitously, discover this. It'll just come into our telescope and whatever. But no, it's actually painstaking to build an apparatus for a specific purpose and interpret those data in a way that can be then digested by these brilliant theorists who may or may not have come up with some idea to explain them ahead of time, but increasingly look to explain things after the fact. And that's becoming more and more common in physics.
Well, go ahead.
No, I was just going to say that's a wonderful experience for anybody who has the opportunity to go through and build an instrument. I did the same thing with very tiny things in my PhD. So I was looking at atomic level resolution, and I had to build a microscope to do this. And I think carrying it from start to finish really gives you an appreciation for the fact that at first, when you make discoveries, you don't have an interpretation of them necessarily. And so you kind of, you write a paper eventually and you're going to turn loose your interpretation, but you're saying to the community, hey, what do you guys think this means also at the same time? And I think that's a really beautiful community aspect of the scientific process that's quite functional when things... It's quite functional, ideally, when people, like you said, are rivalrous about it. But oftentimes, there are paradigms that become concretized, and everybody, even your rivals, ends up coming up with the same interpretation, which could lead you down a sucker trail. So there's an interesting catch-22 to it as well.
Yeah, that's a big point in my second book, which is this one here called Into the Impossible, which is kind of a guidebook for graduate students or postdocs or even undergraduates to learn how science is actually done behind the scenes, not really necessarily, really going over the scientific apparatus or the data, but what does it feel like to be a scientist? How do these 9 Nobel Prize winning physicists that I interviewed, how do they go about working with competitors? I mean, a lot of times in order to form a collaboration that is capable of discovering a new particle or faraway astronomical phenomenon, you need to have a huge team, which can only be justified by getting a huge budget, or it's kind of circular. And so therefore you need to work with people that have been your rivals and competitors. And so in this book, I talk about it with, in particular, I remember talking to John Mather, who won the 2006 Nobel Prize for studying the black body spectrum of the cosmic microwave background, which is what I study. And he talks about, listening to your critics and sort of not taking their comments to heart. In other words, if someone criticizes you, you can assess them dispassionately and not emotionally, then you kind of have an upper hand and advantage. And rather than letting it go to your heart, you should maybe assess it in your head, but kind of the full scope of what it takes to collaborate, and knowing that there's still people that think he's wrong. And how does he go about handling things like that? So you're absolutely right. I think taking into account the human side of science is often overlooked, and we never teach it to our students. One of the many things that, at least we don't get to teach it here in San Diego.
I'm fighting for it really hard. I'm teaching like an intro astronomy course, and I'm trying really hard to bring in the way that the ancients thought about astronomy too, because it was so ripe with meaning and humanity originally, which is really funny how it's become so cold and divorced from anything that's happening on Earth, the way that we interpret these stories. And I don't think we can escape it. Like we can say like, oh, we're not going to bring our humanity into the way that we interpret this data, but I don't think that it's totally possible. It's probably safer to just acknowledge that, hey, we have stories that play out on Earth, and we'd like to see them happening elsewhere as well. Right. But I don't know if that's possible. What were you going to say, Anastasia?
I was going to say that there is a way that ideas get really solidified. And so there is this human aspect that you bring into teaching, and there is this process of teaching people how to do science. And this, I think, ties into the first book, Losing the Nobel Prize, which is that what happens when you give a Nobel Prize for an idea to that idea? Like, it feels like it becomes etched in stone. Yeah. And there's literally places where you can go. You can go to tombs of scientists, and their formulas are etched in stone.
Yeah.
And it's it's such an edifice, and it is such a monument that shifting those ideas and going around and being like, okay, well, what if we've given the biggest prize in science for ideas that don't hold? Like, how do you go back on that? It's so embarrassing for everybody
Even if it's
involved.
500 years from now.
Even if it's 500 years from now, right? Like, science is such a discipline of knowledge and of centering yourself in the world, of being able to say things that are true or foundational or whatever you want to call it, that to be like, okay, all that pomp and circumstance, the gold medals, the millions of dollars, mea culpa, sorry guys. It's just like, I cannot imagine that happening, ever.
Yeah, luckily for them, it hasn't happened so much. It hasn't happened, at least in physics, that they've made, true blunders. I mean, they've had some real kind of, I call them bloopers, where they've given it, for example, the 1912 Nobel Prize was awarded to a Swede. And by the way, if you want to up your odds of being a Nobel Prize laureate, try to be born in Sweden, unless it's too late for you guys, because they had something like 3 to 9 times higher rates of winning, at least early on. So now they don't win it so often. But the award was made in 1912 to a man named Gustave Delenn, who invented something that, I know I use every day to this very, day here in San Diego, and it's called a gas regulator for a lighthouse and a buoy. And, I don't use GPS. I don't use my iPhone anymore. I just use these gas regulated lighthouses and buoys to get, nobody uses those. Now, that's kind of, silly. But maybe you think, oh, well, that was back then. It was probably useful. I mean, but how many people could that have, remember, Alfred Nobel wanted the Nobel Prize to only be given to a single person who the previous year had conferred the greatest benefit to humanity. Like, I don't know what people were doing in Kansas with a lighthouse, but maybe, whatever. So maybe they did use it. But the thing that's so kind of just delightfully blooperish of them is that Einstein had created the theory of special relativity 7 years earlier and had not won it. And, it's really kind of a shameful thing for the Nobel Prize Committee in that he was excluded from winning it because he was Jewish. And he was doing theoretical work, which was considered non-Aryan science. And back then, the Aryan movement was everywhere. And so up until the 1930s or so, in fact, his was one of the first that went to purely theoretical, conjectures. His, Bohr's, and a couple others.
Was that anti-Semitic measure introduced later? Because he did win the Nobel Prize for an experimental effort.
No, he won it for a combination. I call it a greatest hits, combination of his work on molecular theory. It's called Brownian motion. He won it for explaining the theory behind a German explained experiment by one of the chief architects. He was actually called the head of Aryan physics. The guy,
Whoa.
Philip Lenard was his name. So he had won the Nobel Prize in 1905, I think, when Einstein had this miraculous year. So Einstein, he eventually won it for something completely unrelated to any of this relativistic stuff that he came up with. And he didn't even win it after general relativity was validated by the 1919 solar eclipse that Eddington observed. He didn't win it until 1921. So so that the anti-Semitism was pretty rife for a long time. Nowadays, they say, the women have only won 4 times. There's only 2 living female Nobel Prize physicists. No blacks, no, real ethnic minorities have won it in any country. And there have been worse, more egregious Nobel Prize errors in other fields, like giving the Peace Prize to terrorists, or giving the medical prize to the guy who invented the lobotomy.
Wait, what terrorist got the Peace Prize?
Yasser Arafat won the Peace Prize. Some say Henry Kissinger, depending on what side of the fence you're on, was committed a lot of atrocities or responsible for it. And they only gave it to him and his North Vietnamese counterpart in an attempt to bring them to the peace table, which they never did. So, as you may know. So anyway, there are much more egregious things than what happened in physics. But who's to say what's happening there is not happening now? But yeah, I think you're right. To say that this is etched in stone, I think it has become somewhat of an idol, which is another way of saying like an icon, something of worship. Even for me, when I've written 2 books with Nobel in the title, and I'm kind of getting sick of it. But the point being, and I've criticized it, and they still keep asking me to nominate winners of it, which I find kind of unbelievable, since I printed their confidential request for me to nominate the winners back in my book in 2018. Anyway, you're right. I think that we hold these people up, and we have a tendency to teach physics as if it's just a string of Nobel Prize after Nobel Prize after Nobel Prize. And even people who admit, like I'm friendly with Lord Martin Rees, who's the astronomer royal of the United Kingdom, and he just wrote a piece last week in Time magazine about the problems of the Nobel Prize. And yet, I don't think he would turn it down if he won it. So I think it has become sort of a secular idol that actually is literally made of gold and is engraven like the second commandment warns us against in Judaism. So anyway, I think it has taken on that status because
so many different cultures have a story of that. Actually, it's not particularly unique. It's almost a universally human story. You can find it in Mesoamerica too. Like if you fly, the Kukulkan story of flying too close to the sun, trying to elevate yourself. It doesn't work out. Basically, it's an archetypical human story. It's like that's right. Not a good idea.
I just like the in the Hebrew Bible in the Old Testament. So you have like the Jews, they get relieved, they have these miracles in Egypt, and then they're freed from their slavery. There's 10 plagues, including the death of only the firstborn Egyptian males and any Jews who didn't put blood on their. Anyway, it's a complete miracle, right? Then the sea is split. And then 3 days later, they're like complaining to Moses, saying, why did you take us out of Egypt? Were there not enough graves there? And it's like we had cucumbers in Egypt, and I'm just like, what? Who's complaining about not having cucumbers when you're free? And I'd rather have no cucumbers and be a free man than be a slave and have. But anyway, then 40 days later, they make a golden calf. It's insane, right? So just a juxtaposition of people always say, oh, I believe in God if He revealed Himself as a miracle just to me, and I even had that debate with Lawrence Krauss on a debate that we had together, and he said the same thing, which is kind of surprising for one of the world's most self-proclaimed militant atheist, he and Dawkins, and he was like the most simple kind of argument for why he doesn't believe in God, because He wasn't revealed to me. And I said, look, you bow down to your different idols. He has a idolatry of the Nobel Prize. And
nice.
So anyway, I think you're right.
How did he take that?
I think he has a tendency to kind of, move on to topics when he's not particularly comfortable. I mean, I haven't been impressed with. I've been on his show, and we do tend to devolve into talking about like non-scientific things, but we do talk about mostly, what I do as an experimental physicist.
What's really interesting is there's a very parallel debate that I'm aware of that's concerning the Medal of Honor in military institutions, because it's a very destructive force. I can't remember the gentleman's name, but who was one of the few people, maybe the only person who lived through the Iraq conflict and got a Medal of Honor. And he did a really wonderful podcast with Jocko the other day. And he was they were discussing the same issue that we talk about with the Nobel Prize with respect to the Medal of Honor, and how it essentially deifies somebody when in reality it's a team effort. No soldiers out there on the battlefield doing everything. And there's this cultural, social need to deify people, though, to focus it on one individual so that we can use them almost and use them as that torch to walk towards. And if only this, and it's kind of sad, because for the people themselves, there's often this, with Nobel Prize winners, they often devolve into all kinds of crazy stuff afterwards. This is like a well-known phenomenon. And unfortunately, it happens with the Medal of Honor too. So I think there is some sort of great disservice we do by not finding a way to honor the team and the team effort, because science is ultimate. Like Einstein had so many amazing collaborators. From what I understand, he wasn't even that great of a mathematician, but he made friends with one, right? Who he was able to communicate his ideas to and ultimately present it in a format that was acceptable to the community.
And this is something we come across a lot too, because one of the points of the project is not to just talk to people who are inside of the academy and are, on the Nobel Prize track or whatever, but also to talk to people that are working outside of the academy who might have criticisms, who might have objections to the mainstream theories. And this is something that we come across all the time, which is like, if you can find a way to collaborate, and if you can find a way to communicate your ideas to people who are interested in developing them with you, then you won't remain in this oppositional phase for forever, because there's definitely people inside of the academy that criticize the mainstream ideas. Like we recorded 2 conversations on the same subject back to back. One of which was with Carver Mead, who's a Caltech electrical engineer. He did a lot of work in the semiconductor industry, and he wrote a book called Collective Electrodynamics. And his point is that light is not what we think it is in terms of this mysterious photon that gets just shot into space. He's like, look, if you look at what Feynman was saying, there's a handshake between atoms. And so light is the interconnection between atoms, and you can interpret the violation of Bell's inequality through that lens, and you get a very, very, very different interpretation of quantum mechanics. And he has a really interesting point. Like I think that if you shift where you're standing, you can diffuse a lot of the spookiness of quantum mechanics. And then the other conversation we had was with somebody who's outside of the academy who's saying the same thing. And it's like, you guys should work together.
Yeah. But they don't, they all have their kind of fiefdoms that they want to maintain. I encounter that a lot. It's like, I don't want to listen to you because if I listen to you, then I'll have to, really potentially upend my own research, and it could change things. And I'm like, you're supposed to be doing this, for a pursuit of truth, right? It's frustrating. Yeah, the kind of, and the worst thing is when you have people like, even my friends, like, I'm very close with Eric Weinstein, and I'm close to Sabina Hassenfelder and Stephen Wolfram and all these incredible theorists. And they all have different theories of the, grand unification, theories of everything, blah, blah, blah. And they don't read each other's work, except Eric. Eric does have a very commanding knowledge of other people's research, but the rest will be like, my research is correct. So, okay, so I don't need to listen to a completely orthogonal pursuit because I'm correct. It's strange. It's a very strange phenomenon. Like, be like, a reporter's not going to read another reporter's research because she reported on the same story as the other one. It's baffling to me. But do
you have a sense for how we can start to reward team playing behavior?
Yeah, Michael. I was just going to say, I think we don't teach the kind of soft skills that you guys have developed. Look, you guys are very good at conversation. You guys are very good at distilling topics down to a simple, succinct question. And you're not just only interviewing, you're also sharing your own journeys and your own personal experience, not your own personal data, but your own personal facts, right? Or objective facts that you have cultivated, right? So we don't teach that to our students. We just don't. And maybe it's because we don't have enough time. Maybe if we, added on an extra year, or as I think we should go to school year round. I don't know why like a college student or my kids don't go to school year round. Other countries do. And it's not like, and they've shown actually the biggest discrepancies between, say, poor kids and rich kids. And sometimes they use poor as a synonym, which I don't prefer for African Americans. And are underrepresented communities. But the biggest difference is that richer children, I'm talking about, kids, school age kids like my kids, they go to school 9 months, and then they have summer enrichment programs. It could be a camp. They found it doesn't matter what they do. They don't have to go to like coding camp for the summer. They can go and like play in a water park. But if they miss out on that interaction, children from lower income backgrounds do not do as well as kids from wealthier backgrounds. And it's a shame, right? Because the student, like, why does I don't get 3 months off over the summer? Why does an elementary school teacher get paid for a full year and then he or she has off for 3 months? They should be in school year round, and that would do wonders for our school system and our education. But if that's good for my school age kids, all the more so for my college age kids. I mean, you're supposed to be a professional. When you're in college, you're gearing up to have a professional career, whatever it is. So maybe if we added an extra quarter per year, you're talking, you're talking about a full school year, more than a full school year, that we could then teach the skills that you guys have had to study on your own. And if you were in the academy, if you were faculty, at least at the R1 type schools where I talk to people and I say, well, don't you feel like you have an obligation to share your work with the public? I mean, you guys were talking like it is optional. I mean, no one's forcing me to do it. but I feel there's a moral obligation that I have. I'm paid by the public to teach, and communicate discoveries that they paid for. I mean, how dare I keep it to myself, right? Just say, oh, well, I'm not good at it. Oh, okay. So I guess you were born knowing, quantum electrodynamics, like you guys are talking. But no, you weren't born at it. You worked at it because you prioritized it and you thought it was important. Why don't you think it's important to communicate to the public? I don't know.
I absolutely love your perspective on this because it's something that we encountered, that I encountered when we were in grad school, which is that we had a course. It was a very short course. I don't even think that it was a full semester, but it was about writing your scientific ideas down. Mm-hmm. And
shout out Mihan Christ.
Yeah, Mihan Christ was the one who taught it, and she was exceptional. Best professor I've had.
But she was just like ruthless. She was just like, this sucks. Like I got back my.
It was at Columbia.
It was at Columbia.
Oh, it was at Columbia. Uh-huh. Okay. Mm-hmm.
Yeah, and I just got. I thought I was I'd published first author papers by the time I showed up to grad school. I was like, I know how to write science, and she was like, this is crap. Like this is garbage. I think I got like a complete F on my first, return of my grant draft or whatever.
But that wasn't. That's true, and she was really good. Right. She was. Enjoys that. But no, my point was the fact that there were people in the class who were like, why should I have to communicate my scientific ideas in a clear way? Like, I understand what's written. Somebody who's an expert in this understands what's written. And it has carried with me that there is this tendency to cloister the ideas tightly. And I think that impenetrability is appealing to people who have, and this is going to sound callous, not great ideas.
Yeah, well, Anastasia, I think you're right. I think to say that, you're kind of almost above the need to communicate, or this is what I get a little bit of. I'm not going to compare myself to Carl Sagan, okay? But Carl Sagan, as you guys know, was really stigmatized for his early outreach, and he pioneered this. And actually, he's the most famous scientist, probably ever in history, because when he did Cosmos, 1 billion people tuned in, and now it's like if a show on cable gets 100,000 people watching it, it's a great hit. It'll never be such a phenomenon because there were only 3 channels back when I was a kid in 1980. So the point being that he was kind of stigmatized, ostracized, and didn't actually make it into the National Academy, despite the fact that he did pioneering work. He actually started the field of astrobiology in a lot of ways, as well as many other things. We don't have to turn this into a worship of Carl, but the point is, back then it was sort of like a serious scientist doesn't do this, and you hear this from Feynman. Anastasia, you brought him up before. You hear him saying when he won the Nobel Prize, someone said, well, can you explain it, like a reporter? And he said to the reporter famously, if I could explain it to you, it wouldn't be worth a Nobel Prize. Now imagine like the reporter's paying his taxes, paying his salary, paying his imagine if you said to your bosses, I'm not speaking to you guys, specifically, but let's say you work at Twitter, and now you say to Twitter, Elon comes by and he's like, what are you up to? And you're like, oh, you can't understand what I'm doing. It's so sophisticated. If I could explain it to you, I wouldn't be able to earn the 6 weeks off paid vacation I get every year. And I've got friends at Twitter, so I'm just giving them a tease. But the point being, nowhere else is that acceptable. And I think we as scientists need to step up and say, maybe include some in our budget, for actually explicating it to the people that. And the funny thing is it'll actually redound to our benefit. It's actually secretly venal, right? Because the more the science is engaged by the public, and there's a thirst for science. Why is there a thirst for science? Because there's so much politicization and polarization and hatred and demonization of the other. And, they say like 50% of people wouldn't let their child date the person of the opposite political party to them. That's insane. So we need a politics-free science zone. And, no one ever looks up at the constellation and says, oh, Orion, he's a Republican. It's totally divorced from any scientific.
He's got a sword. Or wait, it's a bow. Sorry, he's got a bow.
But I think that's what we're trying to do here, which is to be like, it's okay that Orion has a bow, and to really open up the ground to be able to have conversations that are too politicized otherwise. Because as much as you want to have a science that is open and free, I have never met people who are as mean about ideas as scientists. Yeah. Ever in my life.
Well, it's an arrogance, right? So I always say that scientists are quite arrogant because they know what they do is basically fungible. Like I was just in Italy, I was in Florence, and I got to see the Duomo, and I got to see Giotto's portrait of Christ and Mary. and I'm a Jew, right? So, but I'm like, worship it. It's amazing. And if he hadn't done it, like he did stuff that, like, again, I'm not an expert on Christianity, although I was an altar boy in the Catholic Church. I never had a bar mitzvah. Well, we'll get to that some other time. But he was the first to really portray Jesus as a baby. Like before that, Jesus was like this old wrinkled old guy, because he had to be not wrinkled, but he was like a 30-year-old man, like, but on a baby's body. It was very disconcerting. But Giotto in 1300 painted this like photorealistic thing, and it's so beautiful. And I look at that, I'm like, if he didn't paint that, nobody would have ever painted that. And or I saw Venus, the famous Venus on the half shell painting of Botticelli, I think it is. I forget exactly. It's a shame. But the point being that nobody could have repeated that because no one has done it since. But if Einstein didn't come up with special relativity, as Michael was saying, then easily someone, in fact, Marcel Grossman or Poincaré or somebody else, later on, maybe Hilbert, would have come up with it identically. And we would be exactly where we were, maybe a couple of years delayed. But, who cares? I mean, science hasn't discovered or invented a new branch of particle physics since the 1970s. So a delay of a year wouldn't have done anything out of 50 or 150 years.
We've actually invented a branch of material atomics. So just
be on the lookout.
Just be on the lookout. We're coming to a university near you any day now.
Okay.
No, but if you did see a breakthrough, you would almost certainly see it from lots of different groups at the same time. It's like there is this meta level that is absolutely feeding into when these discoveries occur. It's like the
it's called
world.
the zeitgeist.
Yeah, I mean, we can. You can turn it into a spirit of some sort, but the world isn't ready for certain ideas until it is, and then it's like, oh my gosh, two people come up with calculus at the same time. Isn't that weird? And it's like, well, they were in the same world still.
Right.
It's not that weird, actually. People were looking for this problem.
And they were in communication with each other.
Right, there's so much more to it.
Yeah, exactly. Yeah.
Something that I know that you have to go in a little bit, but I do want to open this can of worms so that we have a future conversation, which is that the ideas that Carl Sagan laid out in Cosmos are shockingly central to the world of cosmology today. Like you listen to Cosmos, and Cosmos is basically a primer for what the ideas held today are. I mean, he's got some of the weird stuff about, the weird things that live in the atmosphere of Jupiter.
Yeah.
But beyond that, it's very much...
And even before him, Eddington was kind of the personality also who set up the paradigm that Carl Sagan inherited.
And I wonder, with the James Webb results, is that going to change? That has to change, right?
Mm. Well, I think things are changing. I think that there was a prescience that he had, especially with astrobiology, not as much with cosmology, but certainly with astrobiology, that Carl did really kind of pave the way for. And it's amazing, like the Voyager Golden Disk, I found out when I talked to Andrewian on my podcast, that it was her brainwaves that were recorded, and they recorded the very first ever example of what's called like world music. Like they went around, sampled music from every country on Earth that they could get to. It's like never. Now we just go down to the iTunes store and buy some world music, Putumayo, and I've got some of that. So it's just. His mind was really unrivaled, and he wrote fiction and the Contact, based on my great friend Jill Tarter, her career. So yes, it was really prescient, and he actually did something when his love of Jupiter or whatever, when he was flying or was commanding the Voyager 1 spacecraft. He did two amazing things. One was to look and take a picture of the Earth for the first time. And that was the pale blue dot. And I have a picture of that where he calls it a mote of dust suspended on a sunbeam, which is pretty poetic. But then with the Galileo mission to Jupiter, he turned it around when it was just going around Earth, and he pointed at the Earth. He said, could we see signs of life, as a function of distance from the Earth? And he was really the first person to really think about that with the sensors, on that instrument, and then kind of extrapolating to the exosolar planets, which were just getting discovered. So I think it's quite humbling to think of how much he really did lead the field of astrobiology and deserved to be in the National Academy, and was punished because of his success as a communicator. So that's pretty. And now you see it with people like Neil deGrasse Tyson, who hasn't arguably done as much as a scientist, certainly in 40 years or whatever since his last published paper, but he has done a lot for communication. And why not kind of valorize that in a certain sense. I think James Webb is revolutionizing our understanding of how the universe evolves, and probably will have stuff to say about exosolar planets. They've already discovered carbon dioxide on an extrasolar planet. So there's a question of, what will happen if this pace sort of keeps and continues. And, and at a certain level, it is an evolution of Hubble. It's bigger, it's better, but it's fundamentally similar in that it can see galaxies just like Hubble, but it can see it at higher redshifts because it's an infrared camera rather than a visible light camera, or as a near infrared camera that Hubble had on it. So for all these reasons, yes, we're going to get new glimpses into our understanding of the universe, but to really get an understanding of what the cosmos is doing, in the earliest moments, and understand its origin and its evolution and its composition in the earliest moments, we're talking seconds after the Big Bang or even less. Then you need to do the science that my colleagues and I are doing, which is in the cosmic microwave background radiation. We're building the world's highest, most powerful observatory of its kind, called the Simons Observatory, to look for the signatures of the earliest gravitational radiation that ever existed, properties of galaxies, properties of fundamental particles like neutrinos, and looking for dark matter and its effect on the early universe. And then from that, we can make forecasts as to what the universe will do long into the future, maybe even billions of years from now.
Are those Earth-based experiments or satellites?
Yeah, so the Simons Observatory is in 17,200 feet in Chile in the Atacama Desert, the Andes Mountains. I'm going there in a few weeks to supervise the final acceptance of 3 of the telescopes pointing platforms, mounts. And we'll be then getting first light with the instrument next year and taking data in the form of what's called B-mode polarization data, looking for the imprint of primordial waves of gravity, gravitational waves, not from black holes in our local universe, so to speak, but from the origin of the universe and its violent birth. And we're doing that with 300 plus collaborators on all 7 continents. And it's going to have the most powerful cameras, telescopes, and analysis computing platforms ever deployed.
Why that location to study gravitational waves? Is it an optical phenomena?
So it's looking for their imprint of primordial waves of gravity formed during the hypothetical inflationary epoch that persist to the formation of the cosmic background radiation, which is about 400,000 years after the Big Bang. If inflation occurred, it would be 10 to the minus 36 seconds after the Big Bang. So waves of gravity produced during the inflation epoch live, like photons, live forever. So they can be present when the CMB forms. And then we look at the CMB and we see imprints of it. Now, why high altitude? Why location? Well, we know from going to the kitchen and heating up your coffee cups there that water absorbs microwaves very effectively. So you'd like to be in a place where there's no water in the atmosphere. You'd like to be in space. But space is, as we know from the Webb telescope, at least 100 or 1,000 times more expensive if you can even launch a telescope that big. So our telescope is bigger than the Webb telescope, which had to be origamily unfolded, if that's a word, in this orbit 1 million miles away from the Earth. So I don't think that there's any possibility of even ever deploying a telescope like this to space. And it would be more expensive than every human endeavor in the physics realm ever undertaken. So Chile is one of the driest places on Earth. That means it has very low water vapor. It's kind of like a poor scientist satellite, we call it.
Mm-hmm. Yeah. So what are those? Can you, if you have time, just let us know if you got a split. But
I've got five more minutes or so. Yeah.
5 minutes. Yeah. I'm just curious what, if you can in 5 or less than 5 minutes, break down what that signature looks like. That's new. What does the gravitational imprint on the cosmic microwave look like?
Yeah. So this will be on your video channel too, right?
Mm-hmm.
Yeah.
Okay. So if you take a telescope, here's my handy dandy telescope, and you take a pair of polarized sunglasses and you break them apart, you have 2 Polaroid filters that look like this. So you take these 2 Polaroids. So guys, subscribe to their YouTube channel and hit mine while you're at it. So these Polaroids transmit 50% of the light that's coming into them. And then if you have 2 of them, you can block out 100% of the light because you make them orthogonal to their axis of transmission. So I'm now showing blocking, transmitting, blocking. Mm-hmm. So as I rotate this Polaroid against this Polaroid, every time I rotate it once physically, the amplitude of light and dark oscillates twice. That only happens with polarized light. It's because light is a transverse electromagnetic wave, a spin 1 phenomenon. And because of that, it rotates twice for every physical rotation of 1. Therefore, you can look for things that are polarized versus things that are not polarized. And this instrument, when you couple this to a telescope, so we actually have refracting telescopes just like this, but they're microwave telescopes. Instead of putting your eye on it, we have 10,000 superconducting detectors, cooled down to 0.1 degree above absolute zero. And each one is sensitive to the 2 polarization states of light. When light interacts with matter, it can become polarized. That's why you have polarized sunglasses, because when light hits the ocean, it goes from sunlight, which is unpolarized, to partially polarized. And that's what we call glare. So you can actually block out the glare of half of the light that's coming into your eye, and that makes it easier for you to see fine details. So the lesson is, when light interacts with matter, it becomes polarized, potentially. Now, there's another way you can get a type of polarization when you have this matter present in the early universe. It's if you have waves of gravity. So waves of gravity we know exist from LIGO, but they're produced anytime you have mass in motion that's accelerating. So if you shake your fist back and forth, you're technically making gravitational waves. You can never detect it, but it's possible. Now, when the universe had not just one black hole crashing into another black hole's worth of mass, it had all the mass in the universe, and it wasn't just traveling at 1/100th of the speed of light before, like the LIGO black holes were. It was traveling at the speed of light, or very close to the speed of light, or even faster than the speed of light. We'll talk about that some other time. So, for all these reasons, you have mass in motion with matter, electrons, protons, photons, etc. All the ingredients are there to make for polarized light. If inflation took place. Inflation is what generates the waves of gravity to begin with. So we're trying to use the observations of these ancient photons called the microwave background. Their polarization tells us about the last time that light interacted with matter. That interaction with matter will have a different pattern depending on whether or not the universe has sufficient amounts of gravitational waves. Those gravitational waves could only be produced by inflation. No other model predicts them. And therefore, seeing this type of polarization, as we claimed in my first book, incorrectly, losing the Nobel Prize, that claim was actually heralded as the first discovery of what caused the Big Bang. And so that's why we were thought to be shoo-ins for the Nobel Prize. But spoiler alert, we were undone by microscopic particles of dust called micrometeorites or cosmic dust, which can also make a polarization signal. And by the way, if you go to my website for your podcast listeners, if you go to briankeating.com/list, and you're one of the first 100 people to do that, and you live in the USA, you will receive a piece of space dust. And I'll actually guarantee it. If you guys have, your audience has a .edu account, because I care so much about training the next generation, I'll send you a micrometeorite for sure. So you don't even have to worry about being one of the first people to sign in. So go to briankeating.com/list, put in your .edu. The only stipulation is you have to live in the US, because I can't mail these things.
I'm going to go get one right afterwards. I'm going to put it right here on the front of the desk.
.edu email list. That's right.
All right, Dr. Keating, you have to go. That was an exceptional explanation. That was clear, concise, and well put. I have a tremendous number of questions. I want to talk to you more about what happened in losing the Nobel Prize, about the BICEP telescope, about everything else. We really, really, really want you to come back.
Anastasia, it'll be my pleasure. Hopefully, time permitting, we'll get to do it again. And who knows? I might be out in your neck of the woods at some point in the future. So my mailing list will tell you all my exploits.
Excellent. We're definitely going to be in San Diego, so we might come knocking on your door.
Awesome. Yeah, we could do one in person
in the next 2 months.
Okay. Yeah, let's set it up. Let's do one in my studio here.
That'd be fantastic. Okay. We'll
Great,
see you soon.
guys.
Right,
thank you so much.
Thank you so much.
It was a great time. Bye.
Yeah.